Okay, well, here we are. Let's get started. I wanted to talk today about introductory for search algorithms. We've talked about the no free lunch theorem, and the large language models in all training of neural networks and AI basically is a search algorithm. The reason that it takes lots and lots of electricity to train a good large language model is because the amount of effort that is required iteratively to train it, to optimize it, to find an optimal solution or a good solution at least, is very what takes a very long time. So the domain expertise is very important in this, and the 2017 paper is All You Need Is Attention. Um, and I guess that was named after the Beatles song "All You Need Is Love." Beatles had a song, "All You Need Is Love," do 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 do, and the people that wrote it really liked the Beatles, or at least one of them did. So they titled their paper not "All You Need Is Love," but "All You Need Is Attention." So Beatles fans, okay. Um, you know why Steve Jobs named his company Apple? Because of the Beatles. The Beatles had a recording company called Apple. And so Steve Jobs said, "Ooh, I'm going to call my company Apple, just like the Beatles." If you read his biography, it's a very fascinating biography. He has a lot of idiosyncrasies like Elon Musk and some of the other great people that are entrepreneurs and creators, kind of personality a little bit on the edge. And so that was all well and good because it turns out that in copyright law and trademark law that you can use other people's names as long as you don't conflict with their business. And there was a classic lawsuit of Cracker Barrel. Cracker Barrel used to be a type of cheese. I think it was generated by Kraft. And so you would go into Walmart and you would see this little band of Cracker Barrel cheese. And of course, there's the Cracker Barrel restaurants. And so Cracker Barrel cheese sued Cracker Barrel restaurants. And trademarks are really important. You might think that patents and copyrights are important, but I have heard it said, and I believe it. It was on the web, so it has to be true, that all of the trademarks in the world are more valuable than all the patents in the world because the trademarks are really important for people's identification and trust in products. So, anyway, the Beatles Apple company sued Steve Jobs when Apple started to go into music because all of a sudden there was a conflict. As long as they were overhearing computers and Apple was doing Apple was doing music and one was doing computers, that was okay. But as soon as Apple computers started doing Apple Music, they said, that's not good. And they went to court, and guess who won? Anybody have any idea or no? No idea. Well, it turns out that
The Apple company
the Apple company.
from
No,
Steve Jobs.
no, the Beatles company won, and Apple had to pay them big bucks in order to use the Apple brand, and so they figured out some sort of compromise, but it cost Steve Jobs big bucks. And some of you were at the eBear seminar where my friend Hal Phillip was there. He invented the touchscreen and he sued Apple because Apple used the touchscreen and he won against Apple. So Apple, if you want to sue somebody, sue Apple. They don't know what they're doing. Don't sue Microsoft. They're just full of lawyers. First day I consulted for Microsoft, guess what happened? I talked to lawyers even before I started my work. I went in and they said, this is very interesting. I went in and they said, Dr. Marks, I want you to know everything that you do for consulting, we own. You don't own any of it. I said, well, yeah, I'm kind of selling myself out. So, yeah, I understand that. And the other thing they said, which was I always found curious, they said, and we don't want you to look at any patents while you're doing your consulting for us. No patents. I could read papers, but I couldn't read patents. And do you know why? because the lawyers were afraid. They said, well, here's what they said. When we get sued, and I remember it was always when we get sued, not if we get sued. When we get sued, that and you go down the stand and you're being asking questions, they're going to ask you if you looked at any patents, because if patents come up in the litigation and you were actually aware of another patent that we patented or we are using, then we kick into punitive damages. It turns out that if Microsoft uses anything, um, that was previously patented, they have to pay damages. But if they copied it on purpose as opposed to accidentally, they have to pay what they call punitive damages, which are damages above and beyond, which can be incredibly large. So indeed, they didn't want me to look at patents. I always found that was really interesting. And Bill Gates, who I believe never has done anything creative in his life, um, can you think of anything Microsoft has ever done that has been creative? They steal everything, they borrow everything, they buy everything, they litigate everything. They bought PowerPoint, they bought the first DOS system, they stole Windows from Apple, and Apple sued them. And I'm not sure about the outcome of that lawsuit. They came out with a browser, and the browser was a ripoff on Netscape, and there was a big lawsuit that they went to trial with Netscape, and Microsoft won. Um, Word was a ripoff of Word for Windows, which was before Word. Excel was a ripoff of Lotus 123, which was the first spreadsheet. And so they just borrow stuff. I can't think of anything that they've done which if it's actually been creative in that sense. They're just good business people. They have not so good products sometimes, but they're just good business people. It turns out that when I was in Seattle, Bill Gates's father was a lawyer, and he was a lawyer in a very powerful law firm. I think it was Preston Ellis and Gates, and it was a Seattle law firm. And I'm sure that they relied on the law and lawyers and tech lawyers in order to win a lot of lawsuits. Zuka, you are all blurred. Did you rub Vaseline on your? Okay, I don't know. You don't look like that in person, so you're not a blurred person. So do you think it's your lens, or you just got a bad lens? I guess. Okay, I did think it improved a little bit, but okay. Today I want to talk about the improvement. By the way, sometimes I pause because I edit these tapes and I want my words to edit very nicely. So I'll probably not include this first part about Microsoft because I don't want to get sued. Um, but somebody is doing a transcript of that. So if you want to sell it to Microsoft, that's okay. It's okay. So today we're going to talk about the importance of domain expertise and kind of have an introduction to the idea of search, which is what artificial intelligence is all about. It's about searching, especially in neural networks, searching for the best set of weights that make your neural network perform in the way that you want it to perform. And we're going to go through some classic sort of definitions and begin to illustrate the importance in general of domain expertise in the search algorithm in general. And so let's go ahead and get started. I want to start with something which I find very fascinating. I need a volunteer. Who can be a volunteer for me?
I
Uh,
could, I could.
okay, Riley, you be a volunteer. Do you have a sheet of? Okay, what I want you to do. Can everybody see Riley? Riley, wave your hands. Okay, your background is blurred, so we can't see the paper. You have your
Okay.
background blurred. Okay, so we're going to play a little game here, and I'm going to show off my domain expertise. Are you ready for this?
Hmm.
Okay, Riley, I want you to choose a number between 1 and say 250, okay? And I don't want you to tell me what it is, okay? And I want you to write it down. And I'm going to close my eyes, and I'd like you to write it on a sheet of paper and show it. And then I'd like you to use your fingers. And I'd like you to say, like, if it's 153, you can go 153. So two different ways of doing it. You got it?
Mhm.
Okay. So let's try it. I'm going to look away and you say done when you've communicated the number, and I will illustrate my incredible domain expertise. You ready?
Mhm.
Okay, here we go.
Okay.
Go ahead.
So the number.
Don't mumble it under your breath.
Done.
Okay, you're done. Okay, everybody get the number? Okay, this is going to be a magic trick. So I'm going to share my screen right now. Okay, everybody see the Excel spreadsheet? Can you see it? Can you make out the numbers? Okay, you can. Okay, is the number in the group of numbers labeled A?
No.
Is it in the group of numbers labeled B?
No.
I hope you chose an interesting number. How about C?
Yes.
Okay, it is in C. What about in D?
Not in D.
Not in D. How about in E?
In E, it is not in E.
How about in F?
Not in F.
In G?
Yes.
Okay, is it in hold on a second. Is we just went over G, right?
Yes, sir.
Okay, is it in H?
It is not in H, from what I can
34.
see. Yes.
What do you think? Are you impressed?
All right. So what's the algorithm? Because this is
Exactly. It's not the algorithm, it's my domain expertise. I've memorized all these numbers. And if you identify the columns, I can tell you which number it is. We're going to try it one more time. Okay, Riley?
all right.
Okay, choose an interesting number. Remember our proof that all numbers are interesting? Okay,
All right.
so we have disproved the idea. Okay, so choose an interesting number. Let me know when you're done and you've communicated it.
Sure. So, all right. I have communicated the number.
Okay, okay, let's go A.
Is It's in A.
It isn't. Wow. Okay, it's in
No, it
A.
is. It is.
It is. Okay. Is
It is.
it in B?
It is in B.
Oh my gosh. Okay, it's in B. Um, oh boy. Okay, is it in C?
It is in C.
Holy Toledo. Is it in all of the okay. Is it in D?
It's in D.
Did you choose an interesting number or an obvious one? Is it in E?
It is not in E.
Okay, good. Is it in F?
It is not in F.
Is it in G?
It is in G.
Wow, how about that? Okay, let me think. Okay, is it in that was distraction, by the way. I was trying to make you think that I was thinking about something. Okay, is it in H?
It is in H.
243.
Yes.
What do you guys think? Pretty
All
good,
right.
huh?
What's what's the
Okay,
trick?
so what's no trick? I've memorized it. I have a lot of domain expertise. So I'll make this available to you. See if you can figure out what the algorithm is. This is kind of a detective sort of work. Okay, okay. Arun, you get these all the time. I remember you in the last class I asked quizzes, and you
Oh,
figured them
but
out all the time. Okay, Arun, what is the algorithm?
I might be wrong, but it looks like it's just binary. I think Chris also said it in the chat, right, where the H is the least significant bit. So it's just if the number would be represented in binary, right? Just whatever bits. You had like a seven bit number. That's why the max is
That's right.
255.
That's right. The max is 255, of course, and 2 to what power is 255? or 256, two to the,
Six? No,
yeah,
yeah,
one,
six.
two, three, four, five, six, seven, two to the eighth, I think, right?
Yeah, yeah,
Something
one of
like
those
that.
two.
Okay. Well, that's true. When you're giving me yeses and nos, you're giving me a binary number, like 1 0 1 1 0 1 1 0. Okay. Are you ready for even what is cooler? I just have to add the first number in each column where you said yes. So if we had the number, for example, 129, it's in column A and it's in column H. It's in none of the other columns. 129. So the answer is 128, which is in the upper right corner of the A column, plus 1 in the upper right corner of the H column. So what I was doing when I was responding to Riley's queries was I was actually adding the numbers in the upper right corner of the places where he said yes. And that gets you really, really quickly to the answer. You don't have to get a binary number and then decode it. Isn't that cool? Okay, so that's domain expertise. And so domain expertise is incredibly important in the search algorithm. And you uncovered my domain expertise. So I'm proud of you. Good job. This is the idea of cooking a pancake. So here's your quandary. Your quandary is as follows. You have the batter all mixed and everything, and you want to figure out how long you're going to cook the pancake on side one and side two. So if you've cooked a pancake, you know you pour the batter in and you cook it for a little bit, and then you flip the pancake over, and that's the reason sometimes it's called flapjacks. And you taste it, and you see which settings are the best. Because depending on how long you cook the pancake, well, it depends on how good it tastes. So you apply a fuzzy metric on a scale of 1 to 10 as far as how good the pancake tastes. And you have these four different outcomes. So two of them, side one is kind of um, on a scale of 1 to 10 is 3 and 2, and then there's one here. But the best one is on side 2, where you cooked it for looks like 10 seconds on side 1, and then side 2 was probably 9 seconds, 9 minutes. Um, so here's a question: if you have no domain expertise about pancakes at all, does this tell you anything about which trial you should try next? The answer is no. Now, you might say, well, if the pancake tastes really good, this is probably going to be smooth. And if I changed it a little bit, it might get better, it might get worse. Well, you have an assumption there. And that assumption is that the landscape, the fitness landscape is smooth. You have domain expertise if you can guarantee that things are only going to change a little bit. So underlying, unknown to you, is something called the fitness landscape. And we see the fitness landscape here. And the success, the target is getting 9 out of 10 in terms of taste. And if you hit 9 out of 10, that's good enough. Typically, in optimization and design, we as engineers do not design to the optimum. Rather, we are presented with design criteria. And as long as we meet or exceed those design criteria, we're done. We don't have to get any better because we've met the criteria. And that's fine. So with a 9 or a 10, we're not getting the best necessarily. We're not getting a 10, but if we get a 9, we say that we're okay. And with this fitness landscape that you see here, you can see that there's four different possibilities, four different recipes that will allow us to do that. So if we were to do an exhaustive search on this, we would do what 100 different. There's 100 different recipes here, right? In terms of side one and side two. Now, if we did an exhaustive search, and we usually hit it on the average, so we'd hit it about at 50 on the average. If we just did random search, you just randomly choose recipes and not repeat them. And if we did that, we would, on the average, get it after 50 trials. If we wanted the absolute maximum, we would have to do all 100 trials, because we could do 99 trials and maybe that 100th is the optimum. We don't know without domain expertise. So, so if we want the optimal, we have to do 100. If we just have a criterion, we only have to do about 50. But the thing is when we start out in the search, we have no idea if even an optimal solution exists. Maybe somebody put some I don't know, what can you put in pancake batter to make it taste terrible? Maybe a big cup of radish juice or something like that you put into it, and no matter how you cook it, it's not going to taste good. So there might not be any optimal. Or maybe you just are not discriminating. Maybe you like any pancake that comes out. And so shoot, the landscape then is going to be much different, and you're going to have a lot of successful recipes. So this is what you get if you have 3 ingredients. Now, suppose that there are 3 parameters in your search, and this third parameter is the heat setting. You can set the heat on your stove from 1 to 10. So you can set the heat on your stove from 1 to 10, how long on side 1, how long on side 2. And then what you get now is a search, which is kind of a cube. We have 3 inputs, so therefore we have a 3-dimensional search. And some of those outcomes are going to be okay, and some of them are going to be otherwise. But notice now, instead of 100, what do you have? You have 1,000 possible searches that you can do in order just for these 3 parameters. So this is the search space for cooking pancakes with 3 parameters. So in general, it's a little bit more complicated than that, because not only do you have to do the heat setting, side 1 and side 2, but you got to cook up the batter. You got to figure out how much pancake mix. So here's a list of things, 9 different ones. So pancake mix, how much pancake mix do we use? 1 cup, 2 cups, all the way to 10 cups. How many eggs do we use? No eggs, 1 egg, 2 eggs. How much milk do we do? 1 cup, 2 cup, 3 cups. Water, I don't know, maybe water makes it taste better, not as milky. How many cups of water do we use? Salt, how much salt do we need? 1 pinch to 10 pinches. Butter, how much fresh butter do we melt in the skillet before the pancake batter? And 0 to 9. Side 1, how long we cook it on side 1 is before. How long we cook it on side 2 is before. And then the temperature, the stove setting, as we did before. Now there are 9 possibilities. You notice that with 2 possibilities, there were 10 to the second possible outcomes, or 100. For 3, there were 10 to the 3 possible outcomes. For this, there are 10 to the 9 possible outcomes, or 1 billion possible outcomes for 9 different parameters and searches. And if you'd have no domain expertise, that's going to take you a while if you actually do it. If you do it one at a time. So 1 billion recipes. It's a lot of recipes without domain expertise. And suppose that in order to do this, it takes you a certain amount of time, and to do 9 recipes, it takes you about a third of the year. Every time you add a different ingredient, it multiplies that by 10, doesn't it? So if you have 10 ingredients, it would take you 3.2 years. I'm assuming 9 is a third of a year. So 10 would be 3.2 years. 11 would be 32 years, all the way down to 22, that's a big number, isn't it? 3,168,808,000 different recipes if you had 22 different possibilities. You can see that this is something which grows exponentially in terms of what you search. So the dimension of your search space is, in general, very, very important. And you got to know, you would like to minimize it as you possibly could. But sometimes you can't. But if you can't, this is something which is known as the curse of dimensionality. The larger the dimension of your search space, the more different trials that you have to do. Now, it does turn out that sometimes it doesn't increase that way. Sometimes, for example, your search space can, say, in 3 dimensions, lie on a plane. All your recipes, optimal recipes, would lie on a plane. In that case, that would be different. But we're assuming in general if they're spread out all over the place. So this is something which we simply can't do, and the curse of dimensionality really is a gut punch to us. That's a reason that large language models require trillions of different results to put in to train the large language models. And both OpenAI and Grok have complained that they have run out of fuel to train their large language models. So at least Grok is trying to um, come up with a technique where it can use AI to create new training data. Well, apparently they're not aware of the model collapse, and I don't see this working unless they're doing something I don't understand. I don't see this working. You can't use large language models to create new results to further train the large language model. It doesn't make sense. I recently heard a podcast where they've done a study on use of social media to train these large language models. And guess what happens to this when you use social media? The large language model becomes a blubbering idiot because just like people that go in and watch social media all the time and are addicted to it, you have what they call brain rot. Well, it turns out we're seeing possibilities of brain rot and using social media to train large language models. So anyway, let's get back to cooking the pancake. We have 3 trillion. Is that right? Three. Let's see. It's a billion, a trillion. Let's see. That's a million, trillion. No, million, billion, trillion. Yeah, 3 trillion. 3.16, 3.17 trillion different recipes. There's no way that we can do this without some sort of domain expertise. So this is the algorithm if we were to use evolutionary search. We would have what we call an oracle. Now, the oracle is something that is in the computer. We're going to assume something. We're going to assume that we have an artificial tongue and that we can automate all of this tasting thing. So we have a tongue, and let's just assume that this tongue can rate the tasting of the pancake. So we choose the ingredients and we cook it. We taste the pancake, and the artificial tongue tells us the fitness, and then we use the fitness to do the next step, and we iterate as we talked about before. All design is iteration. So here is this result applied to evolutionary computing. We take a recipe in, so we have n different recipes. We're doing this in parallel. We're doing n different recipes. We take all of these recipes in, and we go through the oracle. What's the oracle? That's where each one of the different recipes is assigned a fitness. And then after we do the fitness, we do the survival of the fittest. We keep the best tasting pancakes, and then we the repopulate the population. I guess that's what you do with populations. You repopulate them. You repopulate the populations with the original best results plus duplication of those best results. And then the bottom here, we go through mutations. What's a mutation? Well, we do a little bit of change. Instead of 1 pinch of sugar, we put sugar. 1 pinch of salt, we put 2 pinches of salt. Instead of 1 cup of milk, we put 3 cups of milk. And so we take all of the recipes and we perturb them a little bit. And then we get a new set of recipes. These recipes are then presented to the oracle. This is evolutionary search, and it does work. And this oracle will tell us the fitness of these new sets of recipes. Then we repeat this ad nauseum. So this is an evolutionary search. You notice again, and I emphasize this, for the evolutionary search, you have to know your target. You have to know what you're looking for. In this case, you're looking for a good tasting pancake, a good tasting flapjack, and that's your target. That's what you want to do. Darwinian evolution has no chosen target. Now,
Dr. Marks,
yes.
just a quick question for your mutation. Are you having any form of filtering to make sure that you aren't repeating recipes?
Not in the generic model. There are all sorts of variations on this. Otherwise, you couldn't write another paper. Okay, there's a bunch of variations. One is called crossover, where you take two very good results and you take part of one's part of the ingredients of one and you swap it with the ingredients of the other. And so that's called crossover. So some people for a long time were saying crossover is the way to go. Well, yeah, maybe. I don't know. It depends. It depends on the problem itself. So no, there's no hard and fast rules. Everybody is doing their own sort of thing in terms of this, in terms of the mutation, in terms of the memory. The challenge with the memory now is that you have to keep track and you have to pl place previous recipes in some sort of place, And then you have the extra computational load of making sure that if you get a new recipe that's repeated, that you don't use it. Okay, so it slows down a little bit of this iteration process. So, and if you take statistics, there is the idea of sampling with replacement and sampling without replacement. You remember that from statistics?
Mhm.
And so Riley's question is basically that um, if we um, if we don't check on previous results, we're doing what? We're sampling
And
without
with
replacement. Yeah. Um, or is it with? We're not
no,
repeating.
not repeating. So it's if you have a check, then it's without replacement because that means you've already done
Yes.
it. So
Yes, that's
this
right.
is
So
without.
it's equivalent to that. And if you're trying to do something statistically, whether you sample with replacement or without replacement. So it turns out evolutionary programming is one of many cases, and we're going to study a couple more, some that are actually a little bit more um, successful than regular evolutionary search. And that is using multi-agents. Many times when we do a search, we just have one guy trying to find out what the maximum is. And you see the guy on the left here is trying to find out what the maximum is. And the maximum in this case is this first peak. There's a false minima, and sometimes you can get in these false minima, which you say, well, in this region here, this is the best we can do. Maybe this is the best result that we can get. So we want to make sure that we don't get stuck in false minima. There's ways to do that. One of which is called simulated annealing, which we'll talk to about that. And simulated annealing is interesting because we borrow the term from metallurgy. And in metallurgy, it turns out that if you take a metal and you cool it just right, you get the optimal performance of the metal. If you cool it too quickly or too slowly, the metal comes out and it isn't as good. And so what that does is it avoids false minima. If you cool it too quickly, you get one false minima. If you cool it too quickly, you get another false minima. And if you cool it just right, you get the best false minima. So we borrowed from the mathematics of this annealing, this metallurgical heat annealing, and have applied it to search so that we don't get stuck in the false minima. So that's the single agent search. And if we do something called stochastic hill climbing, which if we look and see if we're getting better, um, then we're good. And we take that step. If we are not getting better, then we throw that away and we go back to we revert to our original solution and try a step in another direction. So imagine a blind man on a hill. He sticks his foot out, and if the his foot lands on a place which is uphill, he takes the step. If his foot lands on a place going downhill, he returns to where he was and sticks his foot out at another place to see if he can find which way is uphill. Now, this is in contrast to multi-agent search, which has been more popularized as computers have become more and more complex. Evolutionary search is the way that you do this, and I like to think of it as a bunch of people on a fitness landscape, and this fitness landscape is populated by a number of different agents, and these agents are actually talking to each other on walkie-talkies, and they work together in order to find out the best maximum. And so evolutionary search is one of these. We'll talk about a very successful algorithm called particle swarm, which is another one. However, as I mentioned, you cannot assume that steepest descent and these other things work all the time because you have different types of landscape. This is the reason for the need for domain expertise. Take a look, for example, at this landscape. Whoa, you want to find the maximum of this landscape. And if you use steepest ascent and you start at the place where it says start, and you take a step and you go up the hill, and then you take another step and the one more step, you go downhill. So that place you are must be the optimum, but it is a false minima, isn't it? This is a very difficult search space to optimize. And this, by the way, is a jagged landscape. You can read in the caption, formed by the number of ones needed to express an integer in binary form. For example, 67 is 10011 and has three ones. So 67 would have a fitness of 3. So this is a landscape which is very, very difficult. Another place where a more reasonable place, a more realistic place where you can't have steepest descent is in the solution of the Rubik's Cube. Anybody in here able to solve the Rubik's Cube? Okay, a little bit. Well, it turns out if you solve the Rubik's Cube, if you get down to, man, I almost have it. There's just one color out of space. There are two colors out of space. It turns out that that doesn't help you because what you have to do is you literally have to backtrack from that solution and then do in order to get the optimal solution. You just can't get closer and closer. It doesn't work that way on the Rubik's Cube. If you get really close, you actually have to backtrack. So here is a search algorithm wherein steepest ascent or descent isn't going to work. So again, this is the need for domain expertise. We can always assume that steepest descent or steepest ascent, depending on whether you want to maximize or minimize, is optimal. But there's domain expertise there, and that domain expertise is that your landscape is smooth. And it'll work if your landscape is smooth. In case of the previous fitness landscape that I showed you, and the landscape of solving the Rubik's Cube, near is not always better. I'll give you another example, and this is going to Chick-fil-A. You ready for this? Okay, here you are with Chick-fil-A. You're in the car, and you want to get to Chick-fil-A. And you can see where the car is at, and you can see that the car is really close to Chick-fil-A, but you can't get closer. You literally have to go farther away around the block and come back to get to the drive-through. So you actually have to go further away as the crow flies for Chick-fil-A, and you have to go farther away before you actually find the optimal solution. So this is something like the Rubik's Cube. So I'm showing you just some elementary searches wherein one algorithm doesn't work very well. There's another one. What about steepest ascent? Does that always work? Here's an interesting case. Suppose that we have a landscape which is illustrated on the left here, and this is a fitness landscape. And it turns out that this fitness landscape goes up a hill. And we want to minimize this landscape. So we want to find the lowest point. The optimization is either a maximum or a minimum. It's usually minimum when you want to minimize, for example, error. It's maximum when you want to maximize the objective function, maximize the effectiveness, if you will. In this case, we want to minimize this function on this landscape. Well, this landscape goes uphill, but it turns out right at the top of the hill, there is a big well which goes down to 0. In other words, the optimum occurs where the well is at. This is an exaggeration, of course, but you can see that if you go downhill trying to minimize your error, you're going to get further and further away from the optimal. That it's actually better in this case to go uphill to find the well, and then once you find the well, you can fall down the well and get to the minimum. So I'm trying to illustrate the variation of the different results that we can get in terms of search algorithms. One of them, which is incredibly interesting, is something called which is something called evolutionary programming. Imagine, for example, you have a computer program, and you all have programmed in language, but what you want to do is you want to search for an optimal program. And what you do is you begin to change at random some of the statements in your program. Do you think that that's going to work? No, if you take your computer program and you start changing individual lines or individual characters in it, that ain't going to work. In fact, you're probably going to screw it up more than you are going to improve it. It's going to be very rare that you actually improve it, right? So there are people that say that, well, you know, that we should be able to do evolutionary programming where we actually evolve computer programs. And I think by doing it with Darwinian evolution, just with blind sort of search, that there is no way that that can happen. You're going to stick more bugs into your program than ever before. There was a guy named Thomas Ray. He invented a a program called Tierra. And what Tierra did is attempted to recreate the Darwinian explosion. So this program could never crash the way that he wrote it. And the fitness was the amount of computer time that it demanded. And the longer the program, the better. So he began to apply evolutionary search to this, and he found out some interesting things. Initially, some of the programs got a little bit longer in order to capture more computer time. And then something fascinating happened. There was the development of parasites. There were these little programs that attached themselves to the bigger programs. And because they were part of the bigger programs, they gave this illusion of having a better fitness. And then what happened? There were too many parasites, and all the big programs started to die out. I mean, it was really interesting what happened. But in no way was there evolution of a more complicated life form. And Thomas Ray tried a number of different elements, different ways to affect the situation to make it more positive, but none of those worked. And he eventually abandoned it. So even with evolutionary programming at the level of Tierra, it's not going to, it isn't going to work. We wrote a paper on this, and I'll put a reference to it in the video of what the of what the of what the paper was, but it went through the history of Tierra. Very, very fascinating result. Another thing we must remember is that we many times do not have an optimal solution. As engineers, we know that there are often trade-offs in design. Cheap cars aren't safe, and safe cars aren't cheap. I don't know if I told you, but I used to work as a DJ, and we got a copy in from Charlie's Fish Market, believe it or not. And they wrote the copy, and part of their copy was about the expensiveness of meat. Meat at that time was very, very expensive. I forget why, but it was very expensive. And his comment was, cheap meat ain't good and good meat ain't cheap. So that's a Pareto trade-off. And then he finished it with, good meat isn't cheap and cheap meat isn't good, so eat fish. That was the line he wanted in his commercial. So that kind of cracked me up. But that is an example of a Pareto trade-off, and we'll talk about a Pareto trade-off right now. Pareto trade-off is when you do when you recognize that indeed there are trade-offs in your design procedure. Okay, guess what? My computer program. Okay, there we go. So here is here is an example of Pareto trade-off. Remember I talked about the Pareto random variable in the power curve? Yeah, this is the same Pareto. He was a really smart guy. So this is an example. It's kind of pedagogical, but nevertheless, it's pretty good. And it has the safety of a car on the y-axis. It has the cost of a car on the x-axis. And I'm assuming that we can measure the safety in some sort of way, okay, so that we can apply a number to it, either a fuzzy fitness or some sort of quantitative measure. And we get a whole bunch of cars and we plot the cost versus the cost versus the safety of the cars, as you see here with the circles. You can see with the squares that they are actually very important. And if you connect these squares, you get something called the Pareto front. And if you want a really, really cheap car, then you get a scooter, as shown on the left. If you want a car that's kind of safe and kind of not safe, but, well, it's kind of safe, but it's kind of not, won't cost you an arm and a leg, you go with the automobile, shown in the middle. And if you wanted a car that's really, really safe, but which costs a lot, you would get yourself an armored SUV or some sort of thing. So this is a Pareto optimization, and this examines the trade-off between two different parameters in your design. And as engineers, we're faced with this all the time. We're faced with the design trade-offs. So we have the Pareto optimal. We can present the Pareto optimal. In general, we have constrained optimization. What is constrained optimization? Constrained optimization is when we choose a specific value of cost. I know how much I can spend on my car. And then if I choose this value of cost, if you can see my cursor there, I go up and it looks like right here is the best safety I can get for the car. So if I fix the cost, I go up here. This is constrained optimization. And then I can get my Pareto optimal by getting this car, whatever it is. So I project, if you will, upwards onto the Pareto front. And so constrained optimization is what we do many times, constrained by such things, for example, in this case, cost. But the swap, the size, the weight, and what's the other two words for swap? Size, weight, area, and power, I think are the three things. And you want to optimize each one of those, and you can't do it at the same time, so you have to do a compromise. So those are the things that I wanted to cover about search, and just some general comments about search. The idea, again, reinforcing the no free lunch theorem, which says that without domain expertise, you can't apply an algorithm. And we saw many strange fitness functions which conventional algorithms would not work well. And steepest descent and things of that sort, stochastic hill climbing, only apply if there is the prior knowledge, the domain expertise that the fitness function is smooth, and many times it isn't smooth, and many times you have to do other algorithms. We found, for example, the well at the top of the hill. We wanted to minimize the cost function, and doing that is not achieved by going down the hill. You have to go up the hill until you fall into the well. And indeed, there are some search algorithms and search problems that are like this. So these illustrate the no free lunch theorem, as well as the Rubik's Cube and getting to the Chick-fil-A.